So today we're going to go over Chapter 7 from Fundamentals of Fluid Mechanics by Munson et al. In the preceding chapters, we've gone through a lot of exercises in teaching ourselves analytical solutions to problems that are germane to fluid mechanics. This chapter is a little bit different in that we're recognizing the fact that real fluid flows in 3 dimensions, flows that incorporate many different physical phenomena that we don't normally have to consider when we're using something like Bernoulli or the Reynolds transport equation. Many real-world flows cannot be solved by analysis alone, right? In that case, we have to rely on other things, such as experiments, to be able to give us the data to come up with the true solutions to problems that we have. Now, in this chapter, we want to consider some ideas, some techniques that are important to the planning and execution of these experiments, which will give us greater insight into actual fluid flows. And furthermore, we want to be able to correlate the data that we may do in an experiment to that in a real-world situation, right? And so this concept is called similitude. Similitude is measurements made on one system, typically called a model that is used in a lab. So measurements made on one system can be used to describe behavior of other systems outside the lab. So say a real-world application. So for instance, if we're using a wind tunnel, we can take measurements on a small model-sized car, and we want to be able to take that data, say drag force, and be able to extend that to a real situation where if we had a production vehicle. Now, the challenge here is to come up with a set of experiments that we can be able to accurately describe a system, right? A system that would be in the real world. And so in order to go through this and to introduce a new concept, we're going to look at a very classic example of a long, smooth pipe. All right, and so consider this long, smooth pipe, and we want to look at, say, the pressure drop between points 1 and 2. Now, traditionally, we could say, okay, what is that pressure drop going to be a function of? All right, so pressure drop per unit length is going to be a function of a number of different variables. Those variables can be size dependent, they can be fluid properties, and in this case, we can say, okay, the diameter of the pipe is going to be important. The density of the fluid is going to be important. The viscosity of the fluid is going to be important, and the velocity of the fluid is going to be important. So we've basically said, okay, for this problem, we have 5 variables that can vary. Now, this is different, say, from Bernoulli equation, which we could use to solve this, right? We've used Bernoulli to solve pipe flow examples, and we've gone from point 1 to point 2. But what was one of the key assumptions that we had in Bernoulli to use the Bernoulli equation, right? We had one of the big assumptions is that the fluid was inviscid, so it didn't have viscosity. Okay? And so if we want to recognize the fact that real fluids actually have viscosity and will cause a pressure drop as a fluid flows from point 1 to point 2, we need to be able to come up with some way to do this analysis properly. Now, if I was going to do this experiment in my laboratory, right, if I had this pipe and I wanted to be able to find the functional dependence, F, the function of how these different variables affect the pressure drop, then what would I do, right? So the easiest thing to do would be to hold 3 of the variables constant and vary another one, right? And so that's a relatively easy set of experiments to do. So I could hold 3 of the variables on this side constant and vary the 4th and monitor what happens to pressure drop. All right? So for example, if I hold the diameter, the density, and the viscosity constant, and I vary the velocity, what will happen to the pressure drop? The pressure drop will go up as velocity increases. In a similar fashion, if I vary the diameter and I measure the pressure drop, what will happen? Well, as I increase the diameter, the pressure drop will go down, right? And I can go through this for each of the other two examples where I have vary the density and measure the pressure drop, and vary the viscosity and measure the pressure drop. All right, so an increase in density and an increase in viscosity both will increase the pressure drop from point 1 to point 2. Now, what's the problem with this, right? This is a very, systematic way to experimentally tackle this problem, but there's a significant problem. how do I say hold density constant and vary the viscosity? How many different fluids would I have to span a space of holding density constant and varying viscosity, right? So at our fingertips with common fluids, you can look at the tables in the book. We may have 10, 20 different fluids listed, but how many of those have an equal density and then vary viscosity across the range at which we're interested in? It becomes an extremely hard experimental problem to do. All right. So we have this long, smooth pipe, and say we have a fluid flowing through it like water. And what we're trying to do is we're trying to determine the pressure drop per unit length. And we've already discussed that that pressure drop can be affected by a number of different variables, right? We've chosen diameter, density, viscosity, and velocity here. And we talked about the fact that if I tried to design an experiment that captured all 5 of these variables, pressure drop plus these 4, it becomes quite difficult to have like a proper control. Now, what we can do instead, and what the kind of the core focus of this chapter is we can use something called dimensional analysis, right? And so what we can do is we can say, all right, what if instead of 5 variables, I can simplify the system down into something that has 2 variables? So I'll hand you the 2 variables here, and we'll talk about it in depth. Okay, so instead of a complicated function that pressure drop is a function of d, rho, mu, and v, we have this variable is a function of this variable. Now, one of the things you'll notice when you look at both of these relatively complicated collection of terms is if you go through the exercise of looking at the units of each of these, you will find that they are dimensionless, right? And we'll talk about that in depth. But more importantly, if I was going to do this experiment, it would become much simpler because I'm just looking for a function of 2 different variables. So I could take a pipe, a single pipe with a set diameter with a single fluid, so therefore a set density and viscosity, and I could vary the velocity, which occurs in both of these terms, right? And I could measure this functional dependence between this term and this term. Now, what I would do in each of these cases, I would vary the velocity and measure delta p. Move the velocity a little bit, or increase the velocity a little bit, calculate this, measure delta p at that new condition, right? And so what we've effectively done is we've simplified our system down from 5 different variables to 2 different dimensionless parameters. Now, one of the things that I mentioned was that's really nice about this is that each of these terms are dimensionless. Now, when we talk about, when we talk about dimensionless parameters, typically what we do is we try to say, okay, I want to reduce each of these individual variables down to its most fundamental basic dimensions. And there's 2 different basic dimension systems that we use: mass, length, and time, or force, length, and time. And it doesn't really matter which one you use. The textbook oftentimes uses force, length, and time. But we're able to say, okay, say for example, each of these. We'll do one of these examples. So for this term, actually, let me start that over. Running out of space on the side. Let's try that again. So for this parameter, we would have force length minus 4t squared LT minus 1 times length over FL minus 2t. Now, at first blush, some of this may look a little bit complicated, but let's take the easy one first. D, diameter. Diameter could be measured in meters, inches, feet, right? That is a length term. Velocity, that's another easy one. That's a length divided by time, meters per second. Now, some of the more complicated ones, like density here, density can be said as density is mass per volume. Well, mass is force times acceleration, so we could say force divided by acceleration is equal to mass, where acceleration is LT to the minus 2 over L to the third. That would make this equal to FL minus 4t squared, right? And so this term here is exactly what I have here, right? And so this says that I've reduced for each of these variables, I've looked at the number of basic dimensions that can describe them. And if I go through this math, it shows that both force, length, and time, each of these cancel out so that we have a dimensionless parameter. If we could do the same thing for this dimensionless variable, and we could say, there's no units associated. So this would be two dimensionless parameters, and this would be called dimensional analysis, the ability to equate these two parameters, find the function that describes them, which in turn makes our lives much easier than if we had to do this for 5 different variables. All right, so one of the other important things about dimensional analysis, besides the fact that we've taken a complicated system and simplified it down into something a little bit more palatable in terms of experimental procedures, is that a dimensionless parameter, by virtue of it being dimensionless, it doesn't matter which system of units you have, right? So it's independent of the system of units. Now, the next question you might have is, okay, how do we know how many dimensionless parameters that we need? And that brings us to something called the Buckingham pi theorem. Now, the Buckingham pi theorem sounds very high-minded, but it's actually pretty easy to understand. The Buckingham pi theorem says the number of pi terms that you need to describe a system is basically the difference between two things. K being the number of variables needed to describe the system. So in this case, 1, 2, 3, 4, 5, number of variables needed to describe the system minus the number of basic dimensions needed to describe each of those variables. So remember, we needed force, length, and time to be able to describe each of the different variables: diameter, density, viscosity, velocity, and pressure drop per unit length. That required 3 basic dimensions, right? So for our example here, pi is equal to k. K is the number of variables, so we have 5 minus r. In this case, r is equal to 3 because we need 3 basic dimensions. So 5 minus 3 is equal to 2, so we needed 2 pi terms. So that was the 2 pi terms that we just wrote up. Now, it's important to remember that r, the number of basic dimensions, most typically, if we're working in relatively real fluid mechanics systems, there'll be 3 basic dimensions. Now, that doesn't always have to be the case. Sometimes you might need 2, even 1 if you've got a very simple system. But more often than not, you're going to work in FLT or MLT, mass length time, for the basic dimensions. And K depends on the type of system that you're trying to look at. Now, there are many different ways that you can go about saying, okay, once I determine the number of pi terms, what is the pi terms that I need? And for example, we had the pressure drop per unit length. Let me write that relationship down. Now recall we had this relationship. We went from these 5 variables down to these 2 dimensionless parameters, and this made our lives easier in terms of taking experiments. Now, if we were starting from scratch and we had, okay, I have a system and it can be described by 5 different variables. To know the number of pi terms that we need, we can use the Buckingham pi theorem, pi equals k minus r, and we come up with pi for this system because we have 5 variables, 3 basic dimensions, 5 minus 3 is 2, so we need 2. I've handed you these 2 dimensionless terms. The next question you should be asking is, how in the world do we know what the dimensionless parameters are that are needed to be able to describe this system? Now, there are a number of different ways that we can go about this, finding the actual pi terms that are able to describe this system. The one that's introduced in the textbook and the one that I'm going to talk about next is called the method of repeating variables. The method of repeating variables is a very straightforward and easy way to look at it. It's very step-by-step, and we'll go through each of the steps next. It's very step-by-step, and sometimes it's called a recipe to be able to say, okay, here's my system, here's the variables, here's the Buckingham pi theorem, how do I get to this term, and how do I get to this term? So, method of repeating variables. As I mentioned, method of repeating variables is just one of many ways that we can determine what form, what shape, what do the dimensionless parameters that we want to use to describe a system, what do they look like, right? And as I said, method of repeating variables is relatively straightforward. It's a number of steps. In the text, they list 8 different steps that are needed to be able to perform the method of repeating variables. All right? So step number 1 is list all the variables needed to describe your problem, right? And so in our case, we found for our straight pipe flow, it could be diameter, density, viscosity, and velocity. But these can be any geometry, any fluid property, or any external effect, such as pressure, which could affect the system that we're analyzing. So we list all of those variables. Step number 2 is to express all the variables in basic dimensions, right? So we say, okay, for velocity, we express it in basic dimensions. That would be length divided by time. And we do that for each of the variables. This allows us to go on to step 3, which is determine the number of pi terms. What do we use to determine the number of pi terms? We use the Buckingham pi theorem, which states that the number of pi terms required is equal to k, the number of variables needed to describe a system, minus r, the number of basic dimensions needed for each of those variables. So once we have those number of pi terms, the step number 4 is to select a number of independent repeating variables, and the number of those is equal to the number of basic dimensions that we have. So in this case, we have 3 basic dimensions, and I would select 3 of these as independent repeating variables, right? Now, all of the reference dimensions must be included within this set of repeating variables, right? You wouldn't want to collect a set of repeating variables that just had length when the whole system needs to be described by force, length, and time, or mass, length, and time, right? You want to be able to represent all the different basic dimensions in this set of independent repeating variables. And this is kind of user-defined, right? We're able to select these ourselves from the available variables that are needed to describe our system. We also have to be sure that each of these variables are independent, right? We wouldn't want to use something like density, specific weight, and gravity, right, as 3 independent repeating variables, because you can get to one of them via the others, right? And so we may get into a problem if we do that. So that's why I'm saying they are independent repeating variables. And typically, right, and another important thing to note in step 4 is that we're interested in one variable, right? In this case of pipe flow, what are we most interested in? We're interested in the pressure drop. So we do not want to include pressure drop as one of the independent repeating variables. Now, step number 5 is to form a pi term by multiplying one non-repeating variable by the product of the repeating variables. Nice. By the product of the repeating variables, right? And so for this case, we would take one, say, pressure drop, which we have not selected as one of our independent repeating variables. We could take that and we would multiply it by a collection of the other parameters, the repeating variables, to be able to form a dimensionless product, right? And so form one of the pi terms. Step number 6 is to repeat that process by using the remaining non-repeating variable. And so therefore we would end up with, in our case here, for the pressure drop in the pipe, we would end up with 2 pi terms, right? Step number 7 is to check if each of those dimensionless products you have are indeed dimensionless. This is always a good point to check in to make sure that you haven't done any of your math incorrect. And step number 8 is to express these as a function of each other. All right. Now, it's very important at this point to note that, say, I've got pi 1 is a function of pi 2. Right? I have 2 pi terms that I've determined. This function, right, the method of repeating variables does not tell you anything about the functional dependence between the 2 pi terms. What we need to do in that case is actually run the experiment to be able to determine this functional dependence, which will allow us to extend it into other properties, right? And so let's go through the method of repeating variables for our pipe flow example in the next part. All right, so let's go through the method of repeating variables for our specific problem here. So step number 1. Step number 1 is to determine the number of variables needed to describe the system, which we've already written, but I'll write it out here. D rho mu v. Step number 2 is determine, put each of these into its basic dimensions. So delta p unit length, that's force L minus 3. D is L rho F L minus 4 T squared. Mu is equal to F L minus T minus 2T. And velocity is Lt to the minus 1, right? So we put each of these variables into terms of the basic dimensions. Now, step number 3 is carry out the Buckingham pi theorem. So the number of pi terms required is equal to k minus r. It's equal to 5 minus 3 in this case, because I have 5 variables and 3 basic dimensions, so I need 2 pi terms. Now, step number 4, where we select the repeating variables, becomes a little bit tricky. We don't want the repeating variable to be pressure drop, because that's our dependent term that we're trying to solve for. Now, how many of these are going to be repeating variables? Well, the repeating variables has to be equal to the number of basic dimensions. How many basic dimensions do we have? We have 3. So we have to select 3 of these to be the basic dimensions. And another rule of thumb is when choosing these repeating variables, we want to choose the ones that are as dimensionally easy as possible, right? And so in this case, which looks most complicated out of this? Maybe density or viscosity. So we'll choose the 3 repeating variables. So we'll call the repeating variables. We're going to choose those as d, v, and rho. I definitely want to keep diameter and velocity in because they are dimensionally fairly easy, which will make our lives easier. Step number 5 is to form a pi term by multiplying these by one of the non-repeating variables. In this case, we'll use pressure drop, and so we'll say, okay, our first pi term is pressure drop per unit length is multiplied by the diameter times the velocity times rho. And I've included an exponent on each of these, knowing that some of these may be squared or cubed to be able to make this dimensionless, right? And so at this point we can say, okay, how do we determine what these exponents are? What is A, what is B, and what is C? Well, for force, right, and so we can write out this equation as such. So the dimensions of this term right here is FL minus 3 times length to the A times LT minus 1 to the B times FL minus 4T squared to the C. And we know that this is going to be dimensionless. Or at least we don't know it, but that's what we're trying to make it. All right, so we have this equation. So again, we're taking one of our non-repeating variables, multiplying it by a product of all the repeating variables raised to some power. So now our task is to determine what A, B, and C are. Right? So for force, so we'll say for force, force appears one time here, and C times here to be 0, right? So I've got 1 plus C is equal to 0. For the length time scale, where does it appear? -3 plus A plus B minus 4C equals 0. Again, for the length, I've got -3 plus A plus B, and then length is to the negative, so -4C. These all have to sum up to be 0 in order for it to be dimensionless. And for T, -B plus 2C is equal to 0. Okay, so at this point I have 3 unknowns, a system of 3 equations, so I can solve these 3 equations pretty easily. And it turns out like this: if C is equal to -1, 2 times -1 is -2, so B would be equal to -2. So we've got, if I'm solving each of these, if I solve this system of 3 equations with 3 unknowns, it yields A is equal to 1, B is equal to -2, and C is equal to -1, right? And at this point, I have my first pi term. It's delta P, the pressure drop, times the diameter raised to 1, times the velocity raised to the -2, times the density raised to the -1. This gives me my first pi term. All right, for step number 5, we've just gotten to the point where we're able to determine what it is, and we've determined what the exponents for the equation was. And so pi 1 ended up being delta P sub L times D, because it was raised to the first power, rho was to the -1, and V was to the -2, so those become on the denominator. So now I've got my first pi term. Remember, how many pi terms do I need to describe this? I need 2. So step number 6 is to repeat step number 5 for each of the other non-repeating variables, right? And so what's the non-repeating variable that we have from our list here that we haven't used yet? That would be mu, the viscosity, right? And so pi 2 is equal to mu d to the A, V to the B, rho to the C, all over again. If I write this out in terms of the dimensions, F L minus 2T L to the A, T to the -1 B, F L minus 4 T squared to the C, right? And this is going to be equal to F naught L naught T naught, because we are trying to make this dimensionless. You go through the same exercise for each of the basic dimensions. So for force, we've got 1 plus C is equal to 0. For length, we've got -2 plus A plus B minus 4C, length minus 4C, that's correct, 0. For time, 1 minus B plus 2C is equal to 0. Again, we're able to solve this set of 3 equations with 3 unknowns, and this yields the fact that A is equal to -1 for this pi term, B is equal to -1, and C is also equal to -1. Therefore, pi 2 is equal to mu, and since all of these repeating variables are equal to, or to the exponent -1, they all appear in the denominator. We have d, we have rho, and we have v, right? And so now we have our second pi term, right? So we've got pi 1 and pi 2, and what's step number 7? Step number 7 is to confirm that these are dimensionless, and we previously had shown that each of these terms for our smooth pipe flow example are indeed dimensionless. And step number 8 is to say, okay, I know that there's going to be a functional dependence between these, so we'll have something as a function of the other one. I'm going to choose pi 1 to be my left-hand dependent term because it includes pressure drop, which I'm interested in the most. So we'll say -7, or step number 7, check, dimensionless. And step number 8, choosing my dependent variable some function of mu d rho v. Right? And so now I've gone through dimensional analysis. I've used the method of repeating the variables to go from my variables that influence this, to go from this point to be able to get to this point. So instead of just handing it to you, I'm able to determine this. Now, it's relatively easy to imagine that I could do this for any system. I could do this for, say, water going around a bend, right? Or the force on a gate. We can do this for a number of different systems. For drag on a ship, we can do this for a number of different systems. And it's important to note that since you, as the user, as the person that's following this recipe, can do this in a number of different ways, the form of your dimensionless parameters may be quite different than if I was to do it independently from you, right? So there's not a right way to do it, but if you follow these steps, it will be correct, right? There's a number of different ways you can do that, and each of your dimensionless terms may look different, but as long as they are dimensionless and they are done properly and everything balances, you'll be able to know what these pi terms are. And the next step, of course, would be to determine what this functional dependence is between each of these dimensionless terms, and you usually do that through experiments. Now, this seems like a little bit of a cumbersome kind of recipe, but it's very straightforward, it's very easy to do, and it yields reliable results. There are easier ways to come up with each of these pi terms from a very easy system, and the text talks about being able to do this by inspection, where you kind of shorten the number of steps and you use your intuition and your skills to be able to determine what the pi terms might be. Now, that's fine, but for right now, let's stick with the method of repeating variables and use it since it's the most reliable thing. So one of the things that you'll notice once you do method of repeating variables and you go through dimensional analysis is that no matter the types of problems that you have, you will often see that there are common dimensionless groups, common pi terms that appear over and over and over again, right? And so if you're a scientist and you come up with, you're the first one to notice this, the role of one of these pi terms in multiple problems, perhaps you could name it after yourself. And so a number of folks did this, and so they have famous dimensionless groups named after them. And so we can talk about what each of these mean. Now, some of the nice artifacts of these dimensionless groups that you find over and over again is there's some physical meaning, and it's part of our job to understand what the physical meaning is for each of these dimensionless groups. The first one we're going to discuss is the Froude number. So Froude number is equal to velocity over the square root of acceleration of gravity times L. Right? And so if you're doing a problem and this is one of your dimensionless parameters that pop up, this is called the Froude number. The Froude number is an index of the ratio of the force due to acceleration to the force due to gravity, right? And so if you have a problem that that gravity does not play a large role in, then the Froude number wouldn't appear. Take our reappearing example of the smooth pipe flowing horizontally. Did gravity play an important role in that? No, because it's flowing horizontally. And so the Froude number did not appear. However, if I've got a freely falling fluid, gravity is obviously going to be important, and so the Froude number would probably appear in a problem like that. The next one we want to talk about is the Reynolds number. Now, the Reynolds number is probably the most dimensionless parameter that we're going to use in fluid mechanics, and it's a ratio of the inertial forces to the viscous forces, right? So flows characterized by low Reynolds number, meaning lower velocities or very high density or very large viscosity, are slow and creeping flows. On the other hand, high Reynolds numbers flows, high velocities, low viscosities, where Reynolds number could be 1,000, 5,000, 10,000, is characterized by very fast and rapid flows. And so those large Reynolds number conditions show that the inertial forces, this top, the numerator, are dominating. The Euler number is next. All right, the Euler number is a measure of the ratio of the pressure forces to the inertial forces. Now, the Euler number can be as often seen in a couple of different ways. It could be written as delta P over rho V squared. It could even be seen as the pressure minus the vapor pressure over 1/2 rho V squared. And this is also called the cavitation number, but it's just another form of the Euler number. And the Euler number comes up, is used and appears in cases and problems where pressure is going to be very important, especially in relation to the actual velocity of the flow, the inertial forces that are being developed within the system. One that you've probably heard of is the Mach number. The Mach number is essentially a ratio of the velocity to the speed of sound, where the speed of sound is equal to the bulk modulus divided by the density. Right? For the Mach number, velocity divided by the speed of sound, where speed of sound depends on the bulk modulus. So what do you think this is? This is an index of the inertial forces to the compressibility forces, right? So where have you heard Mach number in relationship to? That's the speed at which airplanes could be moving, or jets could be moving, or rockets could be moving. Their velocity in relationship to the speed of sound. So at very low Mach numbers, the inertial forces induced by the fluid motion are sufficiently large, sufficiently large to cause a significant change in the fluid density, right? So you are not able to change the fluid density at very low velocities, and so therefore the Mach number would not be very large. However, the opposite would be true for very high Mach numbers. The Cauchy number is related to the Mach number. It's a ratio of the inertial forces to the bulk modulus. It looks very similar. And the reason I want to discuss it is, what if you were doing a problem? Remember, what we're trying to find is independent pi terms. So if you were trying to solve a problem, would you have both the Cauchy number and the Mach number as pi terms to describe a system? The answer is no, because they are not independent. They are so closely related that you could get to one via the other. So you could not have both the Cauchy number and the Mach number as pi terms to describe a system. Next, we've got the Struhal number. The Struhal number is a measure of the ratio of inertial forces due to unsteadiness, right? So omega, it would be an oscillation frequency. So omega L over velocity. So it's the ratio of the inertial forces due to unsteadiness to the inertial forces velocity. Oftentimes, this is the forces due to local acceleration, oscillations, to the convective acceleration caused by velocity, right? And so problems that are steady flow would not consider the Struhal. However, problems that have oscillations or unsteadiness, Struhal number might be important. The Weber number is another dimensionless parameter that often pops up. And it's an index of the inertial force to the surface tension force, right? Remember, this is the surface tension coefficient. The surface tension coefficient may or may not be important in the types of problems that you're doing, but you may see it come up with, say, capillary flow examples, or where you're talking about bubble formation or droplet formation. However, surface tension, say if you're trying to look at drag force on a tanker barge, the surface tension may not be important, so therefore the Weber number wouldn't be here. Knowing each of these dimensionless parameters and knowing what they're ratios of, which gives you a good idea what types of problems you may use them in, is part of what you learn as you become more experienced in fluid mechanics. And we expect you as students to be able to understand each of these individually and be able to interpret what the types of forces that they're relating. All right, so in dimensional analysis, one of the most important things we're trying to get to is we're trying to have very easy dimensionless parameters that can be related by some function, either f, or more commonly we write that as phi, where we can determine the functional relationship between these. Now, the method of repeating variables, which gives you the pi terms, it does not give you this function, right? And so part of the job as an experimentalist is to determine what this function is. And the difficulty in determining that relationship depends on the number of variables that you have, right? So consider the term where we have a single pi term, right? So say I have a single pi term that's important to my problem. All right, where pi 1 is just a function of pi 2. All right, well, this is pretty easy. If pi 1 is just a function of pi 2, I can say, all right, I vary pi 2, I measure pi 1, and I come up with some relationship that's a function, right? And so it's very easy to say that here's a line that connects pi 2 and pi 1, and so that I've determined the functional relationship between each of these dimensionless parameters. Now, 2 points. While it's very easy to connect these dots and come up with that functional relationship, say it's linear or some sort of a more complicated equation, you may be tempted to say, okay, what if pi 2 is equal to here? Is it easy enough to just extrapolate out down below and above where you varied pi 2? You have to be very careful, because this functional relationship, which you've tested experimentally, does not tell you anything. The functional relationship could have been something like this, right? So you have to be very careful where you interpret this functional relationship, what the limits, what the lower bound and the upper bound is of this functional equation, so that you can interpret this relationship between pi 1 and pi 2. It is only valid between the points at which you test, you vary pi 2 and measure pi 1. Now, there are even cases that are even simpler than this. We could have a dimensionless product that's a function of only a single pi term. That happens, and that would be equal to a constant. And still, we would have to be able to determine what this constant is, and we would determine that experimentally. The next step would be, okay, what if I have 3 terms? What if I have a functional relationship between 3 pi terms? Oops, messed that up. Pi 1 is a function of pi 2 and pi 3. All right. If we have a functional relationship between 3 different pi terms, we would still need to be able to determine this function experimentally. Now, you could visualize this in many different ways. As if you had x, y, and z, you would need to plot that in, say, a surface plot, right? You would plot that in 3 dimensions. You could even plot this using iso lines, where, say, I've got pi 1, pi 2, and then I change and I vary pi 3, that may give 3 different relationships. Right, where I would vary this from, say, C3, C2, and C1 just being constants for pi 3, and I would get different variables for each of the pi 3. So I would have iso lines that are a function of both pi 1 and pi 2, or I could, of course, plot this in 3 dimensions. Say pi 1, pi 2, and pi 3. So this is kind of the power of dimensional analysis. The ability to say, take a very complicated problem that is a function of many variables, simplify it down to a function of less variables that are dimensionless, and then be able to carry out experiments that are then extensible to other systems and other situations for that exact situation, so that you can take this functional relationship between these dimensionless terms and be able to gain information. Now, the next step in this is saying, okay, let's extend this into that concept of similitude that we introduced at the very beginning of this chapter. How do we use these relationships to move between a model and a real-world application?